Welcome, everyone. I'm excited to kick off today's presentation on important formulas in fluid mechanics. On this slide, you'll see the title and subtitle, visualized with practical examples and 3D exploded illustrations. Over the next few slides, we'll explore key formulas, understand their practical applications, and see detailed visualizations to make these concepts clearer. Let's get started. Let's take a closer look at density today. Density, as you'll recall, is a measure of how much mass is contained in a given volume. The formula for density is quite straightforward. Rho equals mass divided by volume, or rho equals m/v. To put this into perspective, imagine we have an example. A 2-kilogram bottle of oil that occupies a volume of 2.5 liters. When we calculate its density, we convert liters to cubic meters. So 2.5 liters becomes 0.0025 cubic meters. Dividing 2 kilograms by 0.0025 cubic meters gives us a density of 800 kilograms per cubic meter. This example highlights how density provides us with a way to compare different materials and understand their properties better. Throughout this presentation, we'll see how density plays a crucial role in understanding the behavior of substances in various scientific and engineering contexts. Let's talk about viscosity, which is a measure of a fluid's resistance to flow. The key equation here is tau equals mu times do/di. In this formula, tau represents the shear stress, mu is the viscosity coefficient, and do/di is the velocity gradient perpendicular to the flow direction. To make this clearer, consider an example. Imagine an oil film sandwiched between two plates. If the viscosity mu is 0.1 pa/s, and the top plate moves at a velocity of 0.5 meters per second, while the gap between the plates is 1 millimeter, we can calculate the shear stress tau. Using the formula, tau equals 0.1 times 0.5 divided by 0.001, which results in a shear stress of 50 pascals. This example helps us understand how viscosity influences the shear stress in real-world applications, and it connects to our overall theme of fluid dynamics by illustrating how internal fluid properties affect flow behavior. Let's take a closer look at specific gravity, which is a useful property when we're comparing densities. The formula for specific gravity is quite straightforward. Sg equals the density of the substance, rho, divided by the density of water, rho water. This ratio helps us understand whether a substance is lighter or heavier than water. For example, if we consider oil with a density of 800 kilograms per cubic meter, its specific gravity would be calculated as 800 divided by 1,000, which gives us 0.8. This means the oil is less dense than water, since its specific gravity is less than 1. Understanding specific gravity is important because it allows us to quickly compare different fluids without needing to know their exact densities every time. It ties into our overall theme of analyzing fluid properties, which is essential in many engineering and industrial applications. Let's take a closer look at pressure. The fundamental formula for pressure is P equals F over A. That means pressure depends on the force applied and the area over which that force is distributed. For example, if you have a force of 500 newtons acting on an area of 0.1 square meters, you can calculate the pressure by dividing 500 by 0.1. This gives us a pressure of 5,000 pascals. As you can see, increasing the force or decreasing the area will increase the pressure, which is a key concept when understanding how pressure works in different scenarios. This ties into our overall theme of how forces and areas influence physical phenomena. Let's take a closer look at hydrostatic pressure. The key formula here is P equals rho times G times H. This equation helps us understand how pressure builds up in a fluid at a certain depth. Rho represents the fluid's density, G is the acceleration due to gravity, and H is the height or depth of the fluid column. For example, if we have a fluid with a density of 1,000 kilograms per cubic meter and a depth of 5 meters, we can calculate the pressure exerted at that depth. Plugging in those numbers, the pressure comes out to approximately 49 kilopascals. This concept is fundamental because it explains how pressure increases with depth in a fluid, which is essential in many engineering and physics applications. Understanding this helps us analyze fluid systems more effectively and design safer, more efficient structures like dams, tanks, and submarines. Now let's take a closer look at Bernoulli's equation. The formula here, which is P/gamma plus V22G plus Z equals constant, is fundamental in fluid mechanics. It essentially tells us that along a streamline, the sum of these three terms remains constant. The first term, P over gamma, represents the pressure head. The second term, V squared over 2G, is the velocity head, indicating the kinetic energy of the fluid. And the third term, Z, is simply the elevation head, showing potential energy due to height. What's really powerful about this equation is how it links pressure, velocity, and elevation, demonstrating how energy is conserved in flowing fluids. For example, when fluid speeds up, like through a nozzle, the pressure drops, or if it moves to a higher elevation, the pressure adjusts accordingly. In our example here, we're solving for P2, the pressure at a specific point after the fluid passes through a nozzle. Understanding how to manipulate this equation allows us to predict pressure changes based on velocity and height differences, key for designing efficient systems. So, Bernoulli's equation isn't just theoretical. It's a practical tool that helps us analyze and optimize fluid flow in many engineering applications. Now, let's take a closer look at head loss, which is a crucial factor in fluid flow through pipes. The formula for head loss, denoted as, is given by this equation, equals F times L divided by D, multiplied by V squared over 2G essentially. This tells us how friction and pipe characteristics contribute to energy loss as the fluid moves. To make this clearer, let's consider an example. Suppose the friction factor, F, is 0.02, the length to diameter ratio, L over D, is 50, and the flow velocity, V, is 3 meters per second. Plugging these into our formula, we find that the head loss comes out to approximately 0.46 meters. This example highlights how various factors, like pipe roughness, length, and flow speed, directly impact energy loss. Understanding these relationships helps us design more efficient piping systems by minimizing unnecessary head loss, which is vital in maintaining optimal flow conditions throughout the network. Let's take a closer look at the Reynolds number, which is a key concept in fluid dynamics. The formula for Reynolds number is ρ equals ρ times V times D divided by mu. To break that down, ρ represents the fluid density, V is the velocity of the fluid, D is the characteristic length or diameter, and mu is the dynamic viscosity of the fluid. This number helps us determine whether the flow is laminar or turbulent. For example, suppose we have a fluid with a density of 1,000 kilograms per cubic meter, moving at a velocity of 2 meters per second, through a pipe with a diameter of 0.05 meters, and a dynamic viscosity of 0.001 Pascal seconds. Plugging these into the formula, we get a Reynolds number of 100,000. And what's important here is that a Reynolds number of this magnitude indicates turbulent flow. This example illustrates how the Reynolds number can guide us in predicting flow behavior, which is essential for designing efficient systems and understanding fluid dynamics overall. Let's take a closer look at the Venturi meter. The key principle behind it is that a pressure drop is proportional to the increase in velocity. In other words, as fluid speeds up when passing through a constricted section, the pressure drops accordingly. This relationship allows us to measure flow rates based on pressure differences. For example, if we observe a pressure difference of 2 kilopascals, or delta P equals 2 kPa, we can use that information to find the flow rate, which is denoted as Q. This method is quite useful because it provides a relatively simple way to determine flow rates without the need for intrusive measurements. Understanding this principle helps us appreciate how flow measurement devices like the Venturi meter operate efficiently by leveraging fundamental fluid dynamics concepts. It ties into the overall theme of our presentation by illustrating practical applications of pressure and velocity relationships in fluid measurement. let's take a closer look at Orifice and Pitot meters, which are essential tools for flow measurement. Here, we see the formulas that help us determine the flow rate and velocity. The flow rate, Q, is calculated using the formula Q equals c times a times the square root of 2g times delta h. The velocity, v, is given by the square root of 2g times h. For example, if the height difference delta h is 0.3 meters, we can find that the velocity v is approximately 2.43 meters per second. In the 3D visual, you can see a pipe section with the orifice plate and Pitot tube sensors attached. These devices measure pressure differences to determine flow characteristics. Understanding these formulas and visual cues is crucial because they form the basis for accurately measuring flow in various applications, tying into our overall theme of fluid measurement techniques. Now let's talk about the buoyant force, which is a fundamental concept in fluid mechanics. The formula for buoyant force, Fb, is equal to the product of the fluid's density, ρ, times gravity, g, and the volume of the displaced fluid, v in simple terms. This tells us how much upward force a submerged object experiences due to the fluid it displaces. For example, if we have a volume of 0.05 cubic meters, we can calculate the buoyant force exerted on it. Plugging in the numbers, it comes out to about 490 newtons. In the visual, we see a cube fully submerged in a fluid. The arrows illustrate the forces at play, the buoyant force pushing upward and the weight of the cube pulling downward. This concept is key because it helps us understand why objects float or sink. The buoyant force depends on the displaced volume, which ties into the overall theme of how fluids influence objects within them. Remember, the larger the displaced volume, the greater the buoyant force, and that's what determines whether an object will rise or sink. Now let's look at the concept of stability. The key formula here is Gm equals Bm minus Bg. Essentially, Gm is the metacentric height, which is a crucial indicator of a ship's stability. To put it simply, Bm is the distance from the center of buoyancy to the metacenter, and Bg is the distance from the center of gravity to the center of buoyancy. In our example, if the Bm is 1.2 meters and the Bg is 0.6 meters, then the Gm would be 0.6 meters. This positive value indicates that the ship is stable, as the metacenter is above the center of gravity. The 3D visual on this slide shows a ship model with the metacenter and the center of gravity marked clearly. This visual helps us understand how the relative positions of these points influence the ship's stability. Remember, a larger GM generally means better stability, but too large a GM can also mean a stiff, uncomfortable ride. So, it's all about finding that balance, especially when designing or loading a vessel. Understanding this relationship is fundamental to ensuring our ships remain safe and seaworthy under various conditions. All right, let's wrap up with a quick summary of some of the most important formulas in fluid mechanics. On this slide, you'll see they're organized into color-coded categories to help us remember them better. First, we have the basic properties, which include density, viscosity, and specific gravity. These are fundamental because they define the fluid's intrinsic characteristics. Next, we have pressure and head, represented by the formulas P and ρ, where pressure and gravitational head are key concepts in understanding how fluids behave under different conditions. Then, we see the continuity equation and Bernoulli's equation, which are essential for analyzing flow rates and energy conservation within fluid systems. Moving along, there's flow energy, power, and measurement. These formulas help us quantify the work and energy transfer in fluid flow. Lastly, we have buoyancy and stability, which are critical when dealing with floating objects or submerged structures, ensuring safety and stability. These formulas are the backbone of fluid mechanics, and mastering them ties everything together, from basic properties to complex flow behavior. Remember, understanding these key formulas not only helps in solving problems, but also in grasping the overall behavior of fluids in engineering applications. So, keep these categories in mind as a reference. They're your quick guide to the core concepts we've covered throughout this presentation.